So here's a second example of testing continuity for piecewise functions. We're going to modify that first example just a little bit to one where we expect it to be continuous. So now it's going to be cosine x coming in from the left, including at 0, and then 1 plus x squared after 0 for x positive. And so here's a sketch of that. Certainly looks like they join up and we should get a continuous function. So we want to show that f is in fact continuous everywhere for all real numbers. Okay, so there's going to be two parts to that. Again, there's the away from the breakpoint and at the breakpoint issue. So there's two parts for away from the breakpoint. So let's say A and like say subpoint 1 will be f is continuous for x less than 0. Well, for x less than 0, strictly less than 0, we are nowhere near the breakpoint. If for any point strictly less than 0, then not only at that point, but on both sides, we're going to be given by cosine x. Okay, so here, f of x equals cosine x at and nearby, and that's pretty crucial, we'll see that in a minute, nearby the point. And that's continuous by our big theorem about library functions. And so we don't have to delve into exactly why that's true. We're going to quote that and say, look, it's just given by cosine x. Coming in from limits from both sides, it's giving cosine x, everything's good. Okay. Similarly, maybe you could say subpoint 2, if x is greater than 0, then f of x at the point in question and nearby on both sides, f of x is 1 plus x squared, and by our theorem, whatever number theorem it is in your book, it's going to be continuous. Okay. So as usual, the interesting point is the breakpoint, or if there's more than one breakpoint, you got to check those. Okay. So you do have to quote this. And one important thing would be if the pieces themselves are nasty functions created in ugly ways, not with our library, then you have to be careful. So for example, if this was tangent x, and I wanted to say, oh, that's obviously continuous everywhere apart from the breakpoint, that's just not true. Tangent x is undefined and has vertical asymptotes, has infinite discontinuities at a bunch of points, at any odd multiple of pi over 2, and so you would get discontinuities there. So be careful here. Don't just assert, just because I have a formula for it, or a name for it, that it is continuous. But these guys, cosine and 1 plus x squared, hey, yeah, definitely. Oh yeah, and of course I raised something. Okay, so here's a function. Okay, so now I'd say part B, at x equals 0. Okay, so we need to trot out the left-hand limit and the right-hand limit. We need to show those are equal to show that there's a limit at all. And we need to evaluate the function at that point, not going to be hard, show that's equal, and then we're going to be okay. So, very similar. Limit as x goes, actually, this is exactly what we did before. Limit as x goes to 0 from the left. Start out by just naming it by its generic name f of x. And then say, oh, because I've specialized to the left-hand limit, to negative values of x, and only because of that, I can replace it with the simpler function cosine. Because when x is coming from the left, it's always cosine. Then you can quote the fact, oh, that's just like we were doing before. That's just like I was just analyzing cosine on its own at 0. That is cosine of 0, and that's 1. Okay, so we got a limit there. And the right-hand limit, start with the same thing, except just right-hand limit. You still need to convince me you are taking the limit of the same function. So don't jump into 1 plus x squared too quickly. But very similar to before. Now that I've said, oh, I'm looking at f, but I'm specifically only looking at positive values, well, that's the function I use. That's the formula I use for positive values. That's continuous if it were on its own sake. So that's kind of like as if it was extending that parabola, and that's 1. Okay. And however you can take this limit, and we'll do the next example with something where we can't just quote, oh, it's a continuous function I can plug in, because sometimes it's more subtle. But here it's nice because the pieces are just plug-in guys. They're continuous functions. Okay, so those are both equal to 1. And, of course, we need to check, did we use the right value at 0? You can have the situation like this, where I kind of have something that really wants to be the value with the left-hand side limit and the right-hand side limit, and yet for some perverse reason I've defined the value to be something different. Honestly, that's really rare, and usually you just say, oh, that was a mistake. But it can happen, technically. Okay, f of 0, well, I'm using cosine at 0, and that's 1. Aha! So, these two things together say that the full two-sided limit exists. And we now know that the value exists, it is defined, and it's equal to that same value. Voila. So f is continuous at 0, at x equals 0, and we already checked all the other points in a much more powerful way, and so it's continuous everywhere. Okay. The pitfall often people get into is at 0, at that breakpoint, it's really important that you need to check what's going on both sides. You can't just be like, well, look, if I am only interested at x, as soon as you write at x equals 0, it's tempting to be like, well, look at the piecewise function. Maybe the only thing I have to pay attention to is that cosine of 0 equals 0, because this equals is here and not here. No, limits are all about what's happening on both sides, sneaking up to it, and so you really have to do something this intricate to do it. Okay, next time we'll do something that's more algebraic and something where we do have to do more work to actually evaluate the limit.